All right, here is part 2 of your week 10 exercise. These are fill in the blanks. I'm recording this just in case. I suspect that we're probably not going to have much time next week, so I wanted to give a little extra time to explain how to answer some of these. So these are all really straightforward review questions. So we have question number 1. A beam of electrons passes through a magnetic field without being deflected. What can you conclude about the orientation of the beam relative to the magnetic field, and ignore any other fields? So we're just thinking about a charged particle, an electron, passing through a magnetic field without being bent. So remember that it depends whether we're going parallel or perpendicular. Okay. We'll talk about this more in our live session next week. But you can go back and try and remember, what direction, what orientation does that electron need to be moving to not feel the effects of the to not feel the effects of the magnetic field. All right. Number 2. Can an electron at rest in a stationary magnetic field be set into motion by the magnetic field? Then what about the electron placed in an electric field? Okay, so remember that magnetic fields affect things that are moving. Okay, and then also remember that electric fields doesn't matter if it's moving or not. Okay, number 3. Why don't we see color at the periphery of our vision? Remember rods and cones. Okay, so rods, remember, pick up light intensity. That's what we're using mostly at nighttime. We can see whether something's light or dark, but it's harder to see color because our rods are firing. Whereas our cones, remember, our cones are the little things in our eyes that see color. So do you think that there are more rods or cones in the periphery of our vision? That should help you there. Number 4. Why do radio waves diffract around buildings but visible light waves do not? Remember that the longer the wavelength, the more diffraction. And it also really depends on if the wavelength, if that's close to the item it's diffracting around, that really affects it too. Think about how short visible light waves are. Nanometers, right? Tiny, tiny, tiny. Radio waves are like a kilometer. They can be a kilometer long, right? So that should help there. Let's take a look at the rest. Question 5. What is the fundamental source of electromagnetic radiation? Okay. Remember the things that make electric fields and magnetic fields. That's literally like what this is asking, right? So this should be a really short answer. Okay, number 6. We speak of photons of red light and photons of green light. Can we speak of photons of white light? Why or why not? Ooh. Okay. Yes, we have colored light. We can have red. We can have green. Red light, remember, has a frequency, and green light has a different frequency. The definition of white light. White light is not on the spectrum of colors, right? It's a mixture of all the colors, right? So when we blend red, orange, yellow, green, blue, violet, indigo, all of those together. Those are what make up white light. So can we pinpoint one photon that has a certain frequency of white? You should be skeptical. Think about that. That should help you on number 6. And question 7, using the de Broglie wavelength, how can we explain why electrons don't spiral into the attracting nucleus? Okay, this one's been tough to understand. According to classical physics, electrons would be constantly emitting light, continuous, right? And remember, light is energy. So as an electron is spinning around the nucleus, according to classical physics, it should just keep continually emitting light, which means the electron loses more and more and more and more energy in this theory, right? As the electron loses energy, it would be losing speed. So imagine like the Earth rotating around the sun, and the Earth is just getting slower and slower and slower. Well, whoa, we're gonna start being sucked in further and further and further into the sun, and we will spiral in and implode into the sun. Same idea, right? We're losing energy, we're losing speed. The electron would spiral into the nucleus. Now, we know this is not the case. That would be the case if classical physics were true with some subatomic particles, but that's not true, right? So remember, every particle has a wavelength, electrons included, right? Electrons follow a pretty little wave pattern depending on their energy level around the nucleus of an atom. And we need to make sure that that wave is complete, right? So there's this like, I don't know if I can draw it. I'm actually gonna, here's what I'm gonna do. I'm gonna pause real quick, and you won't even notice the pause, but I'm gonna pull up an image really quickly and I'll show you. And I'm back. Here's the image I wanted to show you. So remember, electrons follow this beautiful wave pattern depending on their energy level. When that wave is connected, like if these little bands here were connected and turned into the circle right here, the end would match up with that end. There's no weird little gap, right? So we get this continuous wave happening at whatever energy level around the nucleus. So that wave is going to continue. It doesn't have a start, it doesn't have a stop. That means that electron is going to stay in that energy level until it drops or, something happens, whatever, right? But while that electron is in that energy level, it's not going to be emitting light. It's not going to be losing energy. It's going to stay put. Okay, so this is what you should be referring to for that last question. So that's that. That was the last question of the exercise. Let me just pause and come back here. Hang on. Yep, here we are back here. So question number 7, that one explained that. So that is in fact the last question of your exercise. And that'll be the last question of any exercise that you have to do for physics class. So congratulations if you've made it this far. You're doing great. And I will see you next week for our last live session. Thank you.